It's now time to look at some code with a very brief introduction to parallel programming with threads and shared memory. Here is sort of a basic hello world like parallel programming in C++. Most of the examples I will be giving in C++, not because it's particularly sort of better than any language, but it's good in the sense that with the latest standard, which is C++11, threads and concurrency was built into the language, and there are a number of features that are very nice. I'm going to start with the basic threads. So here are three things happening in this code here. The first one is that we have to make sure that we include the threads package to get access to the right functions. With that, we can create a thread variable, type a thread, and the name of the variable is t, and initialize it with the function name to the function that will implement the thread. So this will create a thread that is scheduled by the operating system. The thread will call function hello and start to execute function hello either on the same core, if you only have one, or on another core. In the last statement here, we have to wait for the newly created thread to finish. So the function to do that is called join. So the main thread actually does not do anything except create the thread and join the recently created thread. So we know how to create threads, we know how to wait for threads. Here is a slightly more complicated example, and also more realistic example. It's the single precision floating point dot product calculation. We have two arrays represented by pointers to them here, and we multiply them element-wise and sum up the products into the dot product called sum here. What we can now see here is that the iterations in this for loop, so the for loop is the bulk of the work here. The iterations in the for loop can be done in any order, and in particular they can be done in parallel. So this is an ideal case for something which can be parallelized. We still have to think about how is the work distributed among the threads, and how do you synchronize the results. And it turns out to be pretty complicated. In C++ threads, or in P threads for that matter also, there is no way to sort of communicate the result of a thread function to the main thread that called it. So this means that we need to have a special argument here called sum here that represents the result of the function. So we create an array, sum array, that will hold the result for each thread. Secondly, we need to divide the work. We do that by taking the amount of iterations, which is represented by the variable size. Divide that by the number of threads. That gets us size over number of threads. Iterations per thread. So multiplying that by the thread number for each started thread. So we have a for loop here going from 0 to number of threads. Then we start the first. So basically, we take the array, let's be represented here. We divide it by n thread. Let's say n threads is 4. Then start of for thread 0 becomes here, and end becomes here, which is the start of thread 1, which is the end, and then we have the end of thread 1 here, which is the start of thread 2, and so on. At the end, we have to make sure that if size is not evenly divisible number of threads, that we finish with the right number of iterations. I also have created an array of thread handlers here. So I instead of I populate this array with dynamic allocation of thread objects. So I create the threads here, I put the result for each thread in the sum array element, and then I put the pointer to the handle of the thread in this thread array so that I can join the threads by means of a for loop at the end here. So this works. I've tested it, it works. Bad thing here is that the for loop here contains too little work. It's too little sort of, it's the arithmetic intensity, that is the amount of the calculations done per byte that you have to fetch from memory is too low to make it really useful here. Anyway, but it works in parallel. And the way it works is you have the master thread. I will create a bunch of threads, slave thread 1, slave thread 2, slave thread 3, and a slave thread 4, assuming we have 4 threads. Then the master waits. Slave threads can go on working. 4 threads working now, and then they are done at some point. So this one probably finishes first, and then this one, and then this one, and then depending on how much is to do in the final thread, it finishes here. Then the master thread can join. It can join here, join here, join here. Not until they all 4 have joined, we have finished execution of the program. Note here that there is an overhead of creating the threads, so it's only between here and here that we have full 4 threads working. The master thread is sleeping, but it doesn't really matter. If the time is long enough, then that thread will not really consume any resources. But so the slave threads can, during this time here, totally take over the machine here. But depending on how many threads you want to create and how many threads you want to join and how the load imbalance is, maybe the full parallelism is really not big enough to offset the initialization part here and the join part here. In overall, the problems with this approach is that the concurrency machinery totally overwhelms the useful code. The useful code is here. That's the only thing we have useful. The rest is just machinery to get it working. The work distribution among the threads is static and inflexible. The number of threads is built into the code, it's hardwired, and large overheads of creating and joining threads. And I didn't mention it here, but there might be load imbalance depending on the number of threads and the number of iterations you want to go. And how do you deal with that? Is there a way to sort of automatically balance the load? Well, it turns out it's difficult. It becomes even more sort of concurrency machinery that overwhelms the useful code if you want to do this. Time for a quiz.